So we can start, right?
Yes, yes.
Wanted to talk a little bit about perfect numbers because we didn't have a chance to talk about those. But first, there's an additional remark I wanted to make about these quadratic residues and non-residues. Actually, about the multiplication table mode 11 that we did. If you still have access to it, right? This is the one. And this is something very simple. You can explain this to, say, a child who just knows how to multiply numbers, add numbers, subtract numbers. They don't need to know about quadratic residues and non-residues. So first of all, how you create the table, this is exactly a multiplication table. Take numbers from 1 to 10, 1 to 10, multiply them. But then what we did was any number that was larger than 11, we subtract 11. And we subtract 11 any number of times. So the actual multiplication table will have 10 times 10 is 100. And why do we have a 1 there? 10 times 10 is 1 for us, simply because we took this number 100 and we remove an 11, subtract an 11, and so on until we subtract 99. So we're left with a 1. So this is how you can explain the table to someone who doesn't know about congruencies. Now, the additional remark I wanted to make is, if we look at, or actually two remarks, there is a point that's right there at the center of our table. That's the line between the 5th row and the 6th row. If I look at this line, horizontal line between 5 and 6, and then the vertical line again between the 5th column and the 6th column. Now these two lines intersect at one point. You can show the point. It's right there. Not the square. Yes, that's a 2 by 2 square, and the center, that's a 2 by 2 square that you showed us, and the center of that square is it's our center. What I wanted to emphasize is, even before we color these numbers in any way, there's a symmetry with respect to the center. Any two little squares that are symmetric with respect to the centers will have to have the same number inside. Not only they have the same color, but the actual same number. If I look at this 2 by 2 that you showed us, you have 3 and 3. You see symmetric with respect to each other, with respect to the center, and the other two squares are 8 and 8. And I just wanted to emphasize that this holds true in the entire table. And the reason is, it's simple. Any place in this table, if I have two numbers, A and B, and I multiply them, A times B, it's the same modulo 11 as P minus A times P minus B, or 11 minus A, 11 minus B, in general modulo P. Because P minus A is congruent to minus A, P minus B is congruent to minus B, and when I multiply, then P minus A times P minus B this product is congruent to minus A times minus B. But it's the same as plus AB. So that's why they are symmetric. So for instance, if you look at the first row, they are in order: 1, 2, 3, 4, 5, 6, 7, and 8, 9, 10. And then the last row will have the same numbers in increasing order if you start from the right: 1, 2, 3, 4. Similarly, if I take the second row, the row of 2 is 2, 4, 6, 8, and so on. It's exactly the same thing, the second from the bottom. That row, if we start from the right, it's the same thing. Okay, that's one remark, that we have this symmetry. And the second remark, what happens with our diagonals? There are two diagonals here, this square. So the first diagonal, the main diagonal, is green just by design, because we took all these numbers on this diagonal and we made them green. The second remark was that numbers on the second diagonal, meaning 1 times 10, 2 times 9, 3 times 8, and so on, have the same color. In our case, the color is red. and we have this diagonal 10, 7, 2, 6, 8, and then of course by symmetry with respect to the center. Now, what's the reason? Well, the reason is if I look at the second diagonal, it means that I multiply a number a by p minus a. But p minus a is congruent to minus a, so it's like I multiply a times minus a. So this is minus a squared. No matter what a squared is a quadratic residue. So now the answer depends on minus 1. If minus 1 itself is a quadratic residue, then minus a squared is a quadratic residue. And this holds true for the entire second diagonal. If minus 1 is a quadratic non-residue, then minus a squared is a quadratic non-residue. And this holds true for all a's. So this gives us an entire diagonal that's red. In this case, we work with our prime is 11. 11 is congruent to 3 modulo 4. It's a multiple of 4 plus 3. So minus 1 is a quadratic non-residue. This makes all the numbers of this form minus a squared quadratic non-residues. And this means this second diagonal is red. If instead of say 11 we work modulo 7, then we take numbers from 1 to 6. We take the multiplication table, numbers 1 to 6, multiply them, and then remove multiples of 7, and we get a 6 by 6 square. Again, again on the diagonal, we will have the main diagonal. We have all 6 green numbers. We have 3 numbers that are quadratic residues in the case, and then they repeat themselves. So we have a green diagonal, then we will have 3 green numbers, 3 red numbers on each row. And lastly, if we look at the second diagonal again, it's going to be red because 7 again is congruent to 3 modulo 4, meaning minus 1 is then a quadratic non-residue, so the diagonal will be red. But if you were modulo, say, 13, 13 is a prime that's congruent, that's a multiple of 4 plus 1. In that case, minus 1 is a quadratic residue. So if we work with, say, modulo 13, and we will create this 12 by 12 square with multiplication table, and work with these colors as before, then we'll see that the second diagonal will be green as well. Okay, so these are some additional remarks about quadratic residues and non-residue. Now let's start to talk about about perfect numbers, and we'll need another screen. Yes, another page where we can write some things. So the first part of this talk will make as simple as possible, so then everybody can understand. We don't need to take this class in order to understand what we're saying now. A perfect number is a number like 6. Let's say 6 is a perfect number because 6 equals to 1 plus 2 plus 3. And 1, 2, and 3 are all the divisors of 6 less than 6. So again, 3 is a divisor because 6 divided by 3 is an integer number. 4 is not a divisor of 6 because 6 divided by 4, 6 divided by 4 is not an integer. So 4 is not a divisor. So we can say 6 is a perfect number. If I check, let's check, is 10 a perfect number? For 10 to be a perfect number, 10 will have to be equal to the following sum. 1 plus 2, let's see what are the divisors of 10, and 5. And then 10 has one more divisor, that's 10 itself. We don't add the number itself, just divisors less. So 1 plus 2 plus 5 is equal to 7. So 10 is not, yes. So it's false. 10 equals 1 plus 2 plus 5 is false. Yes. So 10 is not a perfect number. If we check numbers from 1 to 100, we find that there is one more perfect number. And it was known to ancient Greek mathematicians at the time. And it's 28, exactly. This equals, let's see, 1 plus 2 plus 4, any other divisor, 7, yes, and 14. And of course, 28 itself is a divisor of 28, but we ignore that. And this is true. 14 plus 7, 21, plus 4, 25, plus 2, 27, plus 1, 28. This is true. But it's not true for any other number less than 100 or less than 200 or less than 300 or less than 400. Now, we have this theorem. Let's just state the theorem and then very quickly explain what it does. So the theorem is, and it was known to Euclid. So let's say in parentheses Euclid, whether he invented or someone else discovered it and he recorded. But in any case, it was known to Euclid. And it says the following: if P is a prime number such that 2 to the P minus 1 is also prime, right? If you use lowercase, let's do it everywhere. Yes, little p. So if p is a prime number such that 2 to the p minus 1 is also prime, and we know sometimes this happens, sometimes it doesn't happen. I mean, there are prime numbers p for which 2 to the p minus 1 is prime, and there are prime numbers p for which 2 to the p minus 1 is not prime. But for those numbers p, for those prime numbers p for which 2 to the p minus 1 is also prime, then the following number, then the number 2 to the p minus 1 times 2 to the p minus 1, I just repeated myself, but one of these minus 1s is in the exponent, 2 to the p minus 1, the whole thing times 2 to the p minus 1, and now p minus 1 is in the exponent. The exponent is p minus 1. Oh, can you, all right, can you move them around so they are, yeah, right. So so then the number is a perfect number. Okay, now let's check the first few cases before we discuss the proof. The first prime is p equals 2. Let's check. 2 to the p minus 1, but let's put a comma in between. Okay, a comma. Okay, so 2 to the p minus 1 in this case is equal to, it's 2 squared minus 1, and it's 3, and it's also prime. So by Euclid's theorem, this produces a prime perfect number. What is the perfect number in this case? It was 2 to the p minus 1 times 2 to the p minus 1 is equal, in this case, to, well, 2 to the p minus 1 is 3, and 3 times, and then 2 to the 1. So 3 times 2 is 6. That's our number, and that's the first perfect number. Now, next case, another example, p equals 3. In this case, I check again. 2 to the p, so 2 cubed minus 1. What's this? It's 7. And this is a prime number. So now we get another perfect number is 2, yes, so 2 squared. So 2 squared, I mean 2 to the p minus, so 7 times 2 squared, actually. 7 times 4, yes. And that's 28. So that's the next. So see, Euclid can recover those examples in this way. It's the next prime now. P equals 5. And when p equals 5, let's check to see if 2 to the p minus 1. What's 2 to the 5 minus 1? 2 to the 5 is 32, minus 1 is 31, and it is a prime. So now if we compute this number, 2 to the 5 minus 1 times 2 to the 4, so it's 31 times 16, and this equals, let's see, 496. That's why I said up to 400, there's no other perfect number. The next perfect number is 496. Now let's check that 496 is a perfect number. But we will, oh, you're gonna write all the divisors. Hey, wait a minute. Let's think. Let's just write on one line, two lines. Let's list all the divisors of 496. Let's just list divisors. Let's write these in words. List divisors of 496. Now, in order to find divisors, I look at the prime factorization of the number, and we saw that 496 is 31. That's a prime number times the power of 2. Yes, times 16. So 496 is actually equal to this number. Now, what possible divisors we have? We have some powers of 2 that are divisors. So let's, on the next line, let's write these powers of 2, exactly how they are. 1, 2, 4, 1, 2, 4. 4 is a divisor, 8 is a divisor, 16 is a divisor, and that's it. There are no other powers of 2 that are divisors of this number. 32, too big a power of 2. 64, it's too big. Now, on the next line, let's write some other divisors, because 31 is a divisor as well, but we can see that if I multiply 31 by 2, I get another divisor. So that's 62. But instead of writing it like that, I know that you can. Okay, you can write it like that if you want. Yes, and then 31 times 8 is 248, and then 31 times 16. But that's the number. Yes, it's the number. Now let's add all these. How many numbers? Not equal. Let's add all on another line. Let's write another line in which we take the sum. 1 plus 2 plus 4 plus 8 plus 16 plus 31 plus 64, 62 plus 128 plus 248, and we claim that this equals 496. Please don't write other stuff there. Let's just say equals 496. Allow anybody who watches this video to stop the video right now and check this. But I want it can be checked, so it's correct. But I wanted to add these numbers in another way that tells us how to prove the statement in general. So let's first add the powers of 2 separately. So just those numbers that were powers of 2. So 1 plus 2, 1 plus 2 plus 4 plus 8 plus 16. This equals exactly 31 in our case, because 16 plus 8 is 24, plus 4 is 28, plus 2 is 30, plus 1 is 31. So it's interesting. So the sum of powers of 2 gives us our prime number, that's 31, that's in the perfect number, but there's nothing to do with the power of 2 for the moment. So that's a 31. Now, Euclid and ancient Greeks or mathematicians at the time, they knew that if you add the first powers of 2, the answer is always the next power of 2 minus 1. So if I only add 1 plus 2 plus 4, I get 7. That's 8 minus 1. If I add 1 plus 2 plus 4 plus 8, then it's going to be 15, which is the next power of 2, that's 16 minus 1. So they knew this happens always. And it's very easy to prove. It's proved like this. If you add one more, if you add 1 to this number, but don't write anything, just think. So I take 1 plus 2 plus 4 plus 8 plus 16, and I add 1 to this number, then I have 1 plus 1 is 2, plus my 2 over there is 4, plus my 4 there is 8, plus 8 is 16, and plus 16 is 32. So if I add 1 to this number, I get the next power of 2. So it means that if I take just the sum as is, I'm getting the next power of 2 minus 1. Of course, in our class, we prove this differently. It's just maybe we saw this before. It's just a geometric sum. But in the case of 2, it's very easy. You just add 1 to the sum and you get the next power of 2. Now, with this in mind, that the sum of the first powers of 2, it's the next power of 2 minus 1, we can add these other numbers that we have, that we need to add. 31, 62, 124, and 248 on another line as follows. It's 31 plus 62 plus 124 plus 248. I want to write it as follows: equals, and I take 31 as a common factor, and I have 1 plus 2 plus 4 plus 8. So again, the first powers of 2. And they had to be like this because that's how we found these divisors. It was 31 or 31 times the power of 2. Now we know that the sum of these powers of 2 is the next power of 2 minus 1. So 15. So 31, let's write it. I don't multiply it. I write 31 plus 15. So now when I add these two last two lines, I get 31 plus 31 times 15. And this equals 31 times 16. And that's our number, 496. Now let's repeat, and that's the proof in general. Let's repeat this in general. Another line. So in general, let q, little q, be equal to 2 to the p minus 1. Not in the exponent, 2 to the p minus 1. So let's write, q is a prime. So q is a prime. Not 1, but q is a prime by our assumption, and Euclid assumption, that 2 to the p minus 1 is a prime. Also, p is a prime by our assumption. All right. So now our perfect number, our number that I want to show that it's a perfect number, equals, so our perfect number, Pn for perfect number, is equal to, let's see, 2 to the p minus 1 is exactly this q. It's q times, replace that 2 to the p minus 1 by q. So it's exactly q times 2 to the, and probably we don't need the last parenthesis and the first. But, okay. So it's just q times the power of 2. Very similar to what we saw earlier. It was 496 was 31. 31 is now replaced by our q. And then 16 is replaced by a power of 2. So now again, list divisors of our number Pn. Divisors. On the first row, we list divisors. The powers of 2. 1, 2, 4, Let's put 4. Let's put a 4. So then people don't think that it's 1, 2, 3, 4, 5, 6, 7. It's just powers of 2. Up to the last power of 2 that's in the number. It's 2 to the p minus 1. The next line, we list the other divisors. Say the other divisors are q times what's a merge în contează. All right, thank you. So right, it's very hot. Yeah. So thank you. Saying so these are q times 1, q times 2, q times 4. But remember, the last number we don't count because it's our number. So it was exactly the power of 2 was 2 to the p minus 2, not 2 to the p minus 1. Okay, like let's have a look at a few lines above, just so that everybody who's watching can see. You see, when I had 31, it was you took 31 as a common factor, but it was only 31 times 1 plus 2, 3 lines below. Right, it was that you wrote, it's 31 times, yes, 1 plus 2 plus 4 plus 8. because if we put the 16, 31 times 16 is our number that we don't count. Okay, so that's why fewer powers of 2. So now we know how to add the sum of the first numbers, 1 plus 2 plus 4 plus dot 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 plus 2 to the p minus 1. We know it's exactly the next power of 2. So let's take the sum, plus plus and then equals. The numbers are there, we just put pluses. Okay, thank you. Plus plus, and this equals, what's the next power of 2? It would be 2 to the p, right? The next power, but it's 2 to the p, but then minus 1. So again, it's our number q. This equals further, is equals. Yeah. You can add one more equality after 2 to the p, and it's q. Let's have a look above. So that happened before. 1 plus 2 plus dot 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 plus 16, maybe a couple lines above. Yeah, you see, 1 plus 2, yes, we have it right there. 1 plus 2 plus 4 plus 8 plus 16 was the next power of 2 minus 1, but that's our prime number q. It was 31, and now it's q. Good. Next line, we take q as a common factor, as before. It was q times, and then I have powers of 2. 1 plus 2 plus up to, now it's 2 to the, yes, p minus 2. So this equals, let's put a q, and still inside parentheses, we know what happens. It's a sum of powers of 2. It's the next power of 2, but the next power of 2 after p minus 2 is to the p minus 1. And then, of course, a minus 1 outside. So, so this is 2 to the p minus 1 minus 1. Now we sum, yes, we add those two lines. Q plus Q times that. So this equals, let's see what happens. It's, you see what happens? Yeah, okay, I can see that you see, but I don't know if anybody can, if everybody can. Yes, don't. I understand you take Q as a common factor. You say it's Q equals to Q times, and then you have two ways. Either you take Q as a common factor, but then it's in a parenthesis, in larger parenthesis, you have a 1 plus 2 to the p minus 1. Yes, let's write plus 2 to the p minus 1, and then plus minus 1. Minus 1, not plus 1. Yeah, and then a minus 1. So now this one cancels the other one. So this equals, let's not cancel. This equals, so everybody can see what you're doing. So this equals exactly Q times 2 to the p minus 1. Because the plus 1 cancel the minus 1, and it's exactly Q times 2 to the p minus 1. But that's our PN number. That's our perfect number. So indeed, this is a perfect number. And if we look at those lines above, that actually happened. When we took 31 and then times, so the last line was 31 plus 31 times 15. And we took 31 as a common factor, times 1 plus 15 is 16, and that's our number. That's the proof in general. Now, for the second part, we'll try to make this thing as quick as possible. Let's write.
I have one question, Professor.
Sorry?
I just have one question.
Yes.
So Euclid said that any number which is of this form will be a perfect number.
Yes.
And we saw the examples here, 6, 28, 496. But 10 doesn't, so 10 is not a perfect number. But does it mean that there cannot be a perfect number that is not of this form? Or will every perfect number be only of this form?
You anticipated exactly the next theorem.
Oh, sorry. No.
Good,
Okay.
very good, very good. So, first of all, we do not know if there are any odd perfect numbers. So this is an unsolved problem. You can write it as an unsolved problem. Okay. Are there any odd?
What if they're even and not of this form?
We'll talk about that in a moment.
Okay.
First of all, are there any odd perfect numbers? This is probably the oldest unsolved problem in entire mathematics, in the sense that we're only talking about problems that were recorded in writing, of course, because other problems that we don't know about. And there are other, of course, we discussed in our class about other and even more famous problems than this. Trisect the angle and the other things. Okay, but those problems are solved. Not possible to trisect the angle and duplicate the cube and the other thing. Even more famous construction with rulers and the compass too. Given a circle, radius 1, construct a square that has the same area.
Yeah.
So those were not, but those are solved, considered to be solved, and they are solved in the sense that we know the answer and we can prove the answer is negative in this case. It's not possible to construct. But this one, we don't know the answer. If there are any odd perfect numbers, probably not. Nobody ever found any perfect number that's odd. Now, about the other part, even perfect numbers like 10. 10 is not a perfect number. It's not of that form. But are there any even numbers that are perfect that are not of that form specified by Euclid? And that's the content of Euler's theorem. So let's write theorem due to Euler. We discussed another theorem of Euler, but it's just another theorem of Euler. And it says the following thing: every even perfect number is of that form. Is of the form, let's write it again, what the form. Is of the form 2 to the p minus 1 times 2 to the p minus 1 with, or where p is a prime and 2 to the p minus 1 is not, 2 to the p minus 1 is a prime, yes. So if p is a prime but 2 to the p minus 1 is not a prime, this is not going to be a perfect number. Now, how do we prove Euler's theorem? We allow ourselves to use some things that we learn in class. For instance, the sum of divisors. Okay, let's go like this. Let's do the following. Let n be a quickly over the proof. Let n be an even perfect number. Let's write prime factorization of n in this form. N equals, let n equals 2 to the, let's write another. Let n equals 2 to the a, I don't know what the exponent a, times. And now, p1, I don't know what. P1 to the n1, so a1 times p2 to the a2, and so on. pk to the ak. Okay, where p1, p2, pk are distinct, so different primes and distinct odd prime numbers. A prime factorization can, in fact, contain the prime factor 2 to some power, but that's exactly what we did at the beginning. We wrote that first. And we know for a fact that the number is even, by our assumption, that there is a factor of 2 in it. So there is a 2 to the a in there, a larger than or equal to 1. Okay. Now, don't write anything, but just for those who are watching, P1, P2, P3, of course, this is P sub 1, but you don't complicate notation. It's already complicated. It's not P times K, it's P and then it's a subscript K. And the same for the exponent, it's a sub k. Just leave it as is. Now, the sum of divisors, let's write another line. We have a formula that we discussed in class for the sum of divisors. Sum of divisors, and we have this sigma, we denote like this. Let's just write the letter sigma of, sigma, S-I-N, sigma, yes, S-I-G-M-A, of m, sigma of n, of little n, sigma parenthesis little n, yes. Now, that's the sum of divisors, and this will have to equal, if our number is a perfect number, not equal to the number, but equal to 2 times the number. So this equals 2m. Why? Sigma of 6 is 1 plus 2 plus 3 plus 6, plus including in the number. So it has to be 2 times 6. Sigma of 496, our perfect number, latest perfect number that we discovered, it's the sum of divisors less than 46. That's 46 less than 496. That's 496 plus the number itself, which is another 496. So it's 2 times 496. So that's why this. Now, if we recall a formula that we discussed in class, then we have the following equality. So let's write. Start. Open parenthesis is 1. Parenthesis 1 plus 2 plus dot dot plus 2 plus dot 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 plus 2 to the a. Close this parenthesis. Times 1 plus p1 plus dot 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 plus p1 to the a1, right? And then dot 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 other factors. It's not immediately right, the last one. Let's put the last one. 1 plus pk plus pk to the ak. Right. Now this whole thing needs to be equal. Let's not write anything. It's 2 times our m, but I have my, not m, was m or n? N, not m. So it's 2 times, so it's, it's sigma of, put m if you want for the number. Okay. So this equals, let's write the prime factorization of 2m. It's exactly 2 to the next power of 2. It's 2 to the a plus 1. 2 times m, it's 2 to the a plus 1. You can put a plus 1 in a parenthesis. Yeah. Times 2 times, well, the rest of it is just m. P1 to the a1. P1 to the P sub P1 to the a1 times pk to the ak. And so on, pk to the ak. Now, so now what the idea? Okay. So it's equal to this. Now we want to prove that this cannot happen. What cannot happen? Unless we are in our situation. But the product that you wrote there, 1 plus 2 plus 2 to the a, times the other things are equal to that. Now, I want to do the following thing. We know that the sum of powers of 2 is the next power of 2 minus 1. So we can replace 1 plus 2 to the a by just the next power, which is 2 to the a plus 1 minus 1. It's 2 to the a plus 1 minus 1. Minus 1 and remove the other things. Okay, so now I claim, okay. Now, what I'm trying to say is that this product, it's not going to be equal to 2 times m because it's going to be larger than 2 times m as follows. Let's say this product that we just wrote let's think for a second before we write, because now this is important part in the proof. We know that why this proof doesn't work when our number is odd. When our number is odd, we don't have this 2 to the a to work with. Now we have this 2 to the a. We work with it, and we found that we get a 2 to the a plus 1 minus 1. The fact that our initial number, our number, that's perfect number, is assumed to be an even number, we know already that this means that little a is larger than or equal to 1, the exponent. But then a plus 1 is larger than or equal to 2. So 2 to the a plus 1 is at least 2 squared minus 1 then, because I have to subtract. 2 squared minus 1 is 3. So this number, 2 to the a plus 1 minus 1, is an odd number larger than or equal to 3. Okay. If it's an odd number larger than or equal to 3, it has a prime factor. But this product has to be equal to 2 times our m. So that prime factor will have to appear in m. So that prime factor will equal one of those primes, P1 or P2 or PK. P1, P2, P3, and so on up to PK. I don't know which one, but to simplify this discussion, let's assume that it is P1. So on another line, don't delete, please. Don't delete anything. P1 is a divisor. Let's write it like this. Little P1 is a divisor of 2 to the a plus 1, 2 to the a plus 1. No, just 2 to the a plus 1 minus 1. Hey, yeah, 2 to the a plus 1 minus 1. Yeah, minus 1. Right, because that's the number that appears 2 lines above. It's a divisor. Now, on the next line, if the number is a divisor, it's less than or equal. So P1 is, we can write in words, is, or you can just write strictly less, because you have this, is less than 2 to the a plus 1 minus 1. Yes. I write 1 over P1 on the next line. These are several tricks, one after another. 1 over P1 is larger, strictly larger, let's write larger, than 1 over that expression. Okay. Lastly, next line. 1 plus, I add 1 on both sides. 1 plus 1 over P1. 1 plus 1 over P1 is larger than 1 plus the other thing. Yes, is larger than 1 plus. Yes, but what is now the right side? Can you compute this? Don't do anything. Can you only compute another piece of paper? Just think about it. It's 1 plus 1 over this, if you write as a fraction. I claim that this equals exactly, you can just 2 to the a plus 1 equals 2 to the a plus 1 over 2 to the a plus 1 minus 1. Equals 2 to the just a plus 1. That's the numerator. Yes. And then divide by 2 to the a plus 1 minus 1. And it's true, because if you look at this, the numerator is 1 larger than the denominator. So the fraction is 1 plus 1 over this. So I go back. Yes. So now let's see what this means. It means that, but what is 1 plus 1 over P1 equal to? This is 1 plus P1 divided by P1 for the same reason. 1 plus P1, that's the numerator. 1 plus P1, divided by P1. It's strictly larger than 2 to the a plus 1 divided by 2 to the a plus 1 minus 1. Now, if I have Okay, one more thing and we are done. Now, if I have two fractions, you see, this over this is larger than this over this, it means the product of these two is larger than the product of the other two. So let's see what this means. The next line, 1 plus P1 times, yes, the denominator of the other one, times 2 to the a plus 1 minus 1, yes, it's larger than P1 times 2 to the a1. Okay, that's all I needed to see. So now we are done. Why? Let's just read this line. Don't do anything to it. So 1 plus P1 times 2 to the a plus 1 minus 1 is strictly larger than 2 to the a plus 1 times P1. If I multiply, let's just multiply both sides by, say, P1 to the A1 minus 1. So let's write the following on the next line, and then we see why. Okay, let's open parentheses and let's write P1 to the A1, P1 to the A1, and then minus 1, A1 minus 1 in the exponent, minus 1 in the exponent. Yes, minus 1.
P1 to the A plus 1, you mean?
No, just as is. A1 minus 1 it's the exponent. Yes. It's P1 to exactly this. Let's put in parentheses. Plus P1 to the A1.
What exactly?
Just A1. This whole thing. Now let's have a look at it. How do I find this? I got it from the line above, which is 1 plus P1. I multiply 1 plus P1 by my number P1 to the A1 minus 1. And then I got this, P1 to A1 minus 1 plus P1 to the A1. This thing now next times 2 to the A1 minus 1 times the next 2 to the A1 plus 1 minus 1. Yeah, exactly what it was above.
Just a second, Professor. We are not using A1, we are just using A.
Oh, yeah, that's A. Sorry, you're right. 2 to the A. No, P1 is still to the A1 minus. But let's, okay. Let's remove this last line. Sorry. Let's remove this last line. As I can see, because we don't have these subscripts and so on. And I want to look at, let's not write anything. It's just let's just look at the equality that we had before. Can I have a look at, let's go above. Can I have a look at these equalities? And I have the following. One line you wrote the following. 2m equals 2 to the a plus 1. Can you see that? Can you highlight it in blue color as you did before? Say, yeah, that line. Either one of those lines.
Okay.
That line. That's our number 2 times m.
Yes.
Now, this equals what's on the next, what is on the next line. So this equals, let's highlight it. Let's make that next line blue and stop right there. Let's make it blue, this, and just have a look at it. So we have blue equals blue. Forget about everything else. What I'm trying to say is the following. Don't make anything blue.
This is the same line.
Yeah, okay. Yeah. So you have 3 blue lines. The first line says 2m equals something, and the next 2 lines together say something else equals the same 2m. Now, what I'm saying is the following. The second line and the third line together, when you multiply them, is not equal to 2m. It's going to be strictly larger for the following reason. if you look at 2 to the a plus 1 minus 1, that's in blue, and then you multiply by 1 plus p1 plus p1 to the a1, just look at this. The first two factors are, the first factor is 2 to the a plus 1 minus 1. The second factor is 1 plus p1 plus p plus p1 to the a1. What are the first two factors on the line above? 2 to the a plus 1, and the next factor is p1 to the a1. I claim that the product of the first two factors on the next, on the second blue row is larger than the product of the first two factors on the first blue row. The product of the factors on the first blue row is 2 to the a plus 1 times the p1 to the a1. The first two factors on the second row is 2 to the a plus 1 minus 1 times 1 plus p1 plus the powers of p1 up to p1 to the a1. How do I know that this product is larger than that? I look at what I wrote what we wrote on the next page, and that's exactly what it is. You see what we wrote? We wrote that 2 to the a plus 1 minus 1 times 1 plus p1 is larger than p1 times 2 to the a plus 1. So now we see that it's the same thing, basically. If you don't agree that it's the same thing, let's have a look. Yeah, the powers of 2 are the same. You see it's 2 to the a plus 1, and then 2 to the a plus 1 minus 1. Yes. But the powers of p1 are not the same. Because here I have a p1. On the last line we wrote, it's a p1 on the right of the inequality, and on the left is 1 plus p1. You see? Right. These are not exactly our blue parts, but they are close to them. Because if I multiply both of them by a p1, I'm getting a p1 square on the right and p1 plus p1 square on the left. If I multiply by p1 square, I'm getting p1 cubed on the right and p1 cubed plus p1 square on the left. And this is exactly part of what we have on the blue line. Let's just leave it at this, and those who really want to check this, they can check. The product of the first two factors on our blue line is, on our first blue line, it's smaller than the product of the first two factors on the second blue line.
Yes.
Okay. Maybe someone will need a piece of paper and a pencil to compute this, but it is smaller. Yeah. Not only this, but the next factor is smaller than the next factor. The last factor, and so on, all the factors are smaller. The last factor on the first row, first blue row, what is that? It's pk to the ak. But what is the last factor on the next row, on the third row? Isn't this 1 plus pk plus da 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 plus pk to the ak? So pk to the ak appears again as just one of those terms. You have more terms. So you will agree that you have more terms, so it's larger than this.
Yes.
So if we put everything together, you cannot have 2m equals to the first row and then 2m equals to what's on the second and third row. What's on the second and third row, it's larger. So that's my conclusion, that we cannot have any perfect numbers, even perfect numbers at all. But that no perfect, no even perfect numbers at all by this proof. But there must be something wrong with the proof, because we know that there exist perfect numbers, only those of that form. So now we see that we didn't have an option to write larger than or equal. So we wrote strictly larger in several places. So the only option when we don't get a contradiction is when all these strict inequalities happen with equality. and then we get equality. All right. Now, for this to happen, let's see where we have some inequalities. When we say, you see a few lines above, you say P1 is a divisor of 2 to the a plus 1 minus 1. And then we say that P1 is strictly less. We did have strict inequality unless we are exactly in that extraordinary situation when that number 2 to the a plus 1 minus 1
is 1.
That cannot be 1 because our number is, so we show that is a prime. But that number is a prime, and P1 is that prime. So when we have equality P1 equals to 2 to the a plus 1 minus 1, that number has to be a prime. 2 to not P1 is not. P1 has to be equal to 2 to the a plus 1 minus 1. P1 equals 2 to the a plus 1 minus 1. Minus 1, yes. And no other primes are allowed except for in the prime factorization, except for 2 and except for P1. No other primes. And why is that? Because when we look, for instance, PK is not allowed to exist there. Because we compare, when we say the last factor on the first row is strictly smaller than the last factor on this, you see, PK to the AK. That's less than 1 plus PK to the AK. So that's why it cannot be there at all. So P2 is not there, P3 is not there, PK is not there, just one of them. I don't know if it was P2 or P3 or PK, but once we made it as P1 assumption that we denote it by P1, that's the only one that appears there. So in conclusion, the prime factorization of our number has to be of this form. In conclusion, Pm has to be right. It was 2 to the a, and then times P1, just P1, because it was P1 to what power?
1.
Just P1 alone, yes. There are no other powers. That number had to be a prime and had to be equal to P1. Otherwise, again, if P1 appears with a, if you get a P1 cubed, then the first blue row will have just a P1 cubed, but the other blue row will have 1 plus P1 squared plus P1 cubed will be larger.
Yes.
So the only option is when that P1 appears. So our number is exactly like that. But then if that's the case, why don't I simplify notation and I write little a equals P on another line. On yes, a equals P, comma, and then what is P1? P1 is 2 to the not A equals P. A plus 1 equals P.
Yes.
A plus 1 we denote by P, and then comma, and then our P1 is equal to what? Is 2 to the P minus 1. Okay, stop right here. Why do I allow myself to denote it by P like it's a prime? Because we proved that when we discussed powers of 2 minus 1, that you cannot get a prime unless the exponent was a prime. So that's why I denote a plus 1 by a prime, because otherwise there's no chance for this 2 to the a plus 1 minus 1 to be a prime. So a plus 1 itself had to be a prime. And if a plus 1 itself is a prime, I denote it by P. So I have P is a prime, but also P1 was a prime, and that's 2 to the P minus 1. So P is a prime, P has to be a prime, 2 to the P minus 1 has to be a prime, and our number was then equal to, let's write the number. The number was equal to 2 to the A, but then 2 to the A is exactly 2 to the P minus 1, because A is P minus 1. If A plus 1 is P, and then times 2 to the A, 2 to the P, and then a minus 1. Yes, it was P1, but we replaced this by 2 to the P minus 1. So yes, indeed, Euler proved that if there is that all the even perfect numbers have to be as specified by Euclid. That's the end of the proof. It will be the end of the video. It looks like a more complicated proof, and it is a more complicated proof.
So this is always going to be a Mersenne prime.
Oh yes, Mersenne prime.
Okay.
That we discussed in class.
Yes.
Let me add with very short story as usual now.
Okay.
Very short, true story about a time where, this very unusual circumstances, very bad circumstances for us, for all of us, about teaching in less than ideal circumstances. Remember a story that I mentioned some time ago, and it's one of the videos that we'll look at them later this semester, because I think it was after the one about
primitive roots, the dacoits.
Right, when they asked me to go bring a student to school. A few days later, classes start. It's my first, so I graduated. It was a math major. Graduated from the University of Bucharest. That's a faculty of mathematics, how they call it, and I worked for several years as a school teacher. And I go there, and I have lots of classes, probably around 28 hours of teaching per week, maybe 30 hours of effective teaching. But anyway, one of these classes, I go there, our first meeting, start the lecture, I write something on the board, and then I hear a loud noise. I turn and nobody says anything, like a bang. And I turn to the board and I write something else. And again, the same loud noise, very loud noise. And after several more noises like this, or just a few seconds later, I realized what happened. One of the students is jumping up and down with his desk. So I immediately stopped the lecture. I went and I talked to him. He ignored me completely. I asked him why he's doing this. Just ignore me. I remember correctly, he never said one word the entire semester. And then when I see that I cannot talk to him, I talk to the rest of the people in class, the rest of the students, and they tell me, one of them told me, because I asked him, is this the first time that happens, or he did it before? And they said, that's what he does, and there's nothing you can do about it. Other teachers try to discipline him, beat him up, give him bad grades, nothing works. That's just what he does. So I'm going to have to teach like this for the rest of the semester. And I turn and I continue to write on the board and explain things, and every few seconds is loud noise. Now, after a few minutes, I realize that he's moving from his place and he's coming closer. So I just remember like it was yesterday. It was a room, large room, and there were windows on that side, and then the door was on the left side. So I look at them, and he was on the most to the right row, or column, how you want to call it. So he's moving towards the wall, towards the windows, but he doesn't go to the wall, and then he starts coming towards me. And every time he jumps, he gains about half an inch or so, because he doesn't jump up. So he's coming towards me. So I guess other teachers don't ignore him, So then there's some confrontation and whatever happens, happens. But I chose to ignore him, so he's coming towards me. And I realized when I have about 15 minutes or so before he's here. And to think about something, and nothing came to my mind. I couldn't think about something useful to do. And he's coming closer and closer and closer. And I don't know, after 15, 20 minutes or so, he's close to me. He's almost touching me with his desk. And he's coming, still coming, jumping. And I still don't have any idea. And the only thing that came to my mind at that time was to move to the other side of the board. It's a large blackboard. So I go there and I continue to write. Now he turns, and again he comes towards me. But I see he doesn't lift his desk and turn and then come toward me. He jumps like this and turns. So he's playing by the rules, by his own rules, whatever. And he's coming to us. And now there was and now he's coming full speed. In 2-3 minutes, he's right here. I have to do something. And the following came to mind. I show him the time and I said, look, you're jumping for 20 minutes already, which is great, but I'm sure that you're tired by now. Even if you don't talk, I know that you understand what I'm saying. I bet that you're not able to return to your place before this class ends. And I started to write other things on the board. So he turns quickly and he goes quickly and he's there before the class ends. He doesn't say anything. But other people told me he's here. He was able to return. And that was the end of the first lecture. And I said, okay, it was a great performance. And I left. Next day I come, I look at him, I start to teach. I write things on the board and nothing, no noise. I'm happy. I said, okay, at least we can teach. At least I can teach and then people can listen. Write some things, everything was fine. Second lecture. Third lecture, I come and I'm very confident. I go there, write on the board, let's continue with the problem we started last time, whatever. Again, the same noise. I turn and I look at him, and he jumps again. And he jumps again exactly in the same way as the first day of classes. He jumps, he moves away, he comes towards me, he comes next to me, I move to the other side of the blackboard. He comes to me and I had to say something else. So he comes and I say, oops, 20 minutes, you're improving. Maybe today you will be able to break your own record, which he did. Fourth day of classes, true story. Fourth day of classes, he doesn't jump. I can teach. Fifth day, he jumps. So then I realized, and I don't understand why he's jumping. There's nothing anybody can do. He jumps, but he doesn't jump every day, but every other day. Now, unlike in our case, when we when we take exams, and we don't decide what the dates for the exams are at the beginning of the semester, when we see that we are ready with part of material, then we take a midterm exam, and later on when we see we're ready, we take another. At that time, you have to write you have to plan ahead and the dates for each lecture and what you're going to say each lecture and when you'll have exams and quizzes like this. First time we had an exam, bad luck, is on the day when he jumps. So he doesn't write anything. He just takes a piece of paper, doesn't write anything on the piece of paper, and he starts to jump like this. No name, nothing. He comes, he's able to, so he holds the piece of paper in his left hand together with holds the desk, somehow he's able to jump. But that's somewhere in the middle of the semester, and he's better by that time at jumping. And at some point he dropped the piece of paper on the floor. I don't remember if he dropped it when he tries to throw it on my desk. But anyway, he goes there and he picks it up. Like you watch this old Western movies. You watch Western movies. Clint Eastwood and other people. Able. Not everybody is able. You know, you drop your hat, you're able to, you ride a horse, you're able to pick it up. So he's that good. He's able, you know, without touching with his feet, without touching the floor, he's able to pick up the piece of paper and he slams it on my desk. He puts it there. No name, nothing. Now, at the end of the semester, you have to give grades. Of course, if someone doesn't have many quizzes or exams, you have to ask them some questions. That was the rule. Give him a grade. I don't have, in his case, I don't have any grade at all. So I go and try to talk to him again. I say, look, I need to give you a grade here. So you need to tell me something. So you answer some mathematical questions. He ignores me. I said, look, I wish I could give you a passing grade, but I have to have something written. If you don't want to talk, fine. Or if you are unable to speak, okay, write something on a piece of paper. Because it's true that you all broke all these world records, but still we need something. So whatever, you wrote something and I put just the lowest passing grade. Then it was this large notebook, they call it in Romanian a catalog, you know, where we have just a few names on each page, and everybody at the end of the semester you put official grades. And I turn the page and I'm surprised and I see the same name. Hey, wait a minute, this is a mistake. It cannot be. And indeed, I look. That's why I always looked at that catalog, but I never look at the two pages at the same time. So that's why I never realized there are two people, not one. Or his name appears twice with the same name. Something was not right. And I look at the name and the last name is exactly the same. And I look at the first name and then the first name sounds the same, but it was just one letter different. And I asked him, of course he ignored me as usual, but I asked in class, hey, is there a mistake? Why does he appear twice? And then someone tells me, there's two of them. He has a twin brother, and they are identical twins, but they come from a very poor family. Their parents do not have enough money to buy clothes for both of them. So they buy clothes for only one of them, and they send one of them to school. And the next day they send the other to school, so on. True story. So finally I realized there was nothing wrong with him. He jumps every day. It's just that one of them jumps, the other doesn't jump. And that's the end of the story. So we can close this video.